stimuli from the outside world, or because it integrates the thousands of synaptic messages that arrive on its dendrite. And again, every time I think about it, I'm just amazed by that. But now it comes our work as a scientist, right? To try to listen to what neurons say, while animals or humans, there's going to be a lot of human recordings in the course on Wednesday, are actually awake, they behave, they do stuff. Because what we want to understand in last instance, as I said during the introduction, is how the pattern of electrical activity of the brain gives rise to behavior, right? So by now you are sick of me saying this, but you know that neurons communicate with each other through electrical signal, that is the action potential. And if you have done your exercises right, you know that you have basically calculated this time interval here that I'm showing you here. This is actually what happens for the real neurons and not for simulation. Action potential are extremely fast. And then you have, again, a fast return to baseline. So since these are electrical signals, we can use electrodes to record the activity of neurons by recording the changes in this membrane potential that underlies the action potential. And we have seen one example of this recording before. When I told you that the spike was first recorded in the axon of the squid, I was talking about a technique that is called intracellular recordings. In intracellular recordings, you can measure the transmembrane potential by inserting usually a glass pipette into one cell and recording the potential change with respect to an external reference frame, which you can set in the extracellular medium in this case. It would be this ground here. This is the intracellular technique, which is mostly used in vitro preparation. The disadvantages of this technology is that it allows for, the advantages, of course, like that you record the action potential, right? You cannot go cleaner than that. That's the message, and that's what you record. But the disadvantage is that, first of all, nerves are extremely thin. The brain moves a lot, and you would be surprised of how much it moves. You're going to see this tomorrow, but the brain really moves. So if you try to stick with your electrode within the axon, which is already extremely thinner than your hair, who has hair, not me, you will basically not really be able to record anything for a long time. You will lose your recording. I mean, it's extremely complicated. There is one lab in Berlin, the lab of Michael Brecht, who does intracellular recording in vivo, and it's amazing what they do. But most of the time, what you want to do is not really go that, right? Because otherwise it would be extremely time consuming. What you want to do is this, is an extracellular recording. So extracellular recording involves placing an electrode in proximity to the cell and put the reference electrode somewhere else. If it's, again, a slice, it's in the extracellular fluid. If it's a brain, it's in another area of the brain. But you still need to have a reference, right? Because you want to measure change in the potential. This arrangement records the changes in the membrane that happens at the membrane surface rather than across the membrane. So it will not tell you, or will not record the exact form of the intracellular spike, but it will tell you if the cell has fired a spike or an action potential. I'm going to go use spike from now on, and when that event has happened. Now, because in system neuroscience, I told you before that the information that the shape of the action potential carries is minimal, and we are more interested in the temporal profile of activity of neurons. So when the neuron is active, because we want to align it to behavior. That is good enough for us, meaning that what we want to know is if the neuron has fired an action potential or not. We can transform the signal, which is, again, a change in membrane potential, into a binary signal that we tell the cell has spiked or the cell has not spiked. So in the end, what we want to do is to record the time when the neuron is active. The shape of the action potential, we can, for now at least, just discard as information, okay? So the problem is that with the extracellular electrode, you are not picking up the change in the membrane potential between the inside and the outside of the cell. So what are you actually picking up, right? You pick a spike, you have a signal, but what is that signal? What's physically represented? And this is coming from the idea that a neuron, so that the action potential does not just generate a change in the membrane potential at the two sides of the membrane of a neuron, but is also influence the medium that is around the cell itself. So when the axon is at rest, or where the cell is at rest, you are in this condition here, right? This is the axon, this is the extracellular environment, you have positive charges on one side and on the other. This is what we've seen before. At this point, there is basically an equilibrium. There is no current flowing inside or outside of the cell. If the polarity of this changes low in one point, like for example, in this point of the axon, the potential of the membrane at that point changes, right? Because you have a flux of ions. So instead of being positive, it's going to be negative at this point, which means that the fact that you have a negative point here, which we'll call it as a sink, will attract nearby charges, which are positive, to arrive to this particular area, right? So you end up, when you have an action potential in this area, that this is called sink, it's negative, it attracts charges from the two sides of the area where actually the event is happening. And these that are positive are called sources, because they are the source of the positive ions that will move toward the negative area, which is called the sink. Is that something that is clear? Because this is really the physical principle by which we can record something with extracellular recordings in the brain. Okay, I see no questions, so I go. So now suppose that you are in this place, right? I told you about this source. So you suppose that you are recording here and you have an electrode here that is connected to your source. You know, you're recording, I don't know, voltmeter, whatever you have to record the change in voltage. And you put your reference somewhere else, right? In the medium, if it's an in vitro preparation, in another area of the brain, if it's an in vivo. What you're actually recording when you're at this point and an action potential has happened a little bit before, it's a positive deflection of the voltage in this area, because these positive ions here are going to be attracted to this area here, right? So when the area that is just immediately adjacent to your electrode act as a source, you will record a positive deflection of the potential there. As this propagates, because the action potential propagates, the sink will move just below your electrode. And at this point, the charge below your electrode is going to be negative. So you'll see the second phase that is basically a dip of potential at more negative values, right? When this moves again, your membrane just below the electrode comes back positive and act as a source for the sink that is now downstream of the area of the axon where you have your electrode. So you will see a general and late phase increase, which is given by the fact that, again, the area close to your electrode is a source. So you are basically recording the change in the ions concentration or the movement of the ions around your electrode that is given by the passage of the action potential in your neuron. Is that clear? The take-home message is that the action potential recorded extracellularly is different than the one that you record intracellularly. It's different conceptually. On one case, you're recording the change in the membrane potential that is given by the action potential. In the other case, you're basically recording the effect that this action potential has in the extracellular environment. But there are two properties that are very important. The action potential is that large. We have seen it is like, I don't know, 100 milliwatts of difference between the membrane potential and the hyperpolarization. The size of one action potential, extracellular action potential, is smaller than that. It's not as much current as it is if you look at the current that flows to the membrane. The other point is that the action potential shape is very stereotyped. The waveform is always the same. But if you look at the waveform of the extracellular action potential, or if you want the extracellular spike, this depends by a series of factors. Most importantly, the exact geometry of the orientation between the tip of the electrode that is recording the extracellular spike and the neuron itself. This is really a fundamental property that allows us to develop an amazing neuroscience tools that is called the tetrodes, that is able to give us a lot of precision when we want to record spikes into a living brain, okay? So the shape of this event here depends on the relationship between this electrode and this source of charges, right? If the electrode is in this position versus this position, a little bit farther away, a little bit closer, the shapes of these waveforms are going to be different. Are we all on board with this? Because basically, this is the most important concepts that we'll prepare for what we're going to talk next. Okay, so since there are no questions, I'll just move forward. How do you compare the extracellular action spike with the intracellular spike? This is a very nice recording done, I think, either in the 80s or in the 90s by the Bujaki lab, in which they had the ability to record at the same time from one neuron with an extracellular electrode. In this case was a tetrode, but just hold your thoughts until this, and an intracellular pipette. So in this case, you see this neuron that was filled after recording, that where we can record both the action potential and the extracellular spike in time. You see that when they're aligned, their profile is very goes synchronously. This increases, this decreases, this increases at the end when this decreases, right? It's really the mirror image. But there are two things that you already see. The first thing is that all the different, these are more than one action potential, but they're extremely precise. So if you overlay one on top of each other, it's really very little deflection from one single thing. Here also you have more of them, but you see how they're different? You see this is very different from this one here. And here you see that they're actually more than one. It's 1, 2, 3, 4, right? So the shape of the action potential, the extracellular spikes, not only depends from the distance and the configuration, but even when the configuration remains intact, it depends from the ionic concentration that is outside of the cell. And again, this is going to be important when we are trying to interpret the recording that we do inside the brain. The other thing is that most of the time you see this profile. This is what electrophysiologists here are really divided in two factions. The one that record extracellular spike and they express them as a negative dip, and the one that instead flip it just to be more similar to the intracellular action potential and that show it as a positive deflection. It's always the same thing. It's just the orientation of the deflection that you actually plot differently, if you're wondering. Anyway, the fact that we actually discard the information because of the shape of the waveform is so unreliable. I told you before, not only depends on the orientation of the electrode versus the neuron, but also on the extracellular medium. So it can change on a moment-to-moment basis. We are going to discard the information about the shape of the waveform almost entirely after we have done our initial recordings. So what we do is that we basically transform, as I said before, the happening of an action potential into a binary event. Either the cell is active or the cell is not active. What I mean is that you have your electrode here, it records the activity from this neuron, in particular from this one that is very close by. You see that you record the extracellular spike here and the profile of extracellular spikes in time. In the end, we are not going to pay attention to this deflection, but we're going to express the activity of this neuron as this series of ticks, because the information that we are caring about is the timing in which this individual action potential or spikes have occurred. Okay, so most of the time, when we're going to analyze our data, we're not really going to look at this, but we're going to look at something like this. In this case, you see that every time, every line in this case is one individual trials. I'll show you on Wednesday what this is. Trust me, this is really cool. And this is something that you can see the timing, the exact timing when the neuron was active. So if you look only at this time course, right? You have that the neuron was active here, 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 here. Then something happened for which this neuron has increased the frequency of his activity over time to go back to level of baseline. This is exactly when they're giving the stimulus, but what this stimulus is, I'm going to tell you on Wednesday. And a plot that is basically expressed like this is called the Russell plot. And this is, I don't know, maybe 90% of the times that you see recording, that's what you're going to see. All right? Okay. So let's go forward now. So I told you that you can record with these extracellular recordings activity of neuron in intact brain while animals are basically doing something. So the beginning, the first type of recordings that we had from the 1950s, again, they were a golden age for neuroscience, the 50s. I mean, really study them, they're really amazing. There is a lot of amazing discoveries done at that time. But what these people did, and these people I'm referring to Hubel and Wiesel, which is one of the most well-known duo in neuroscience, they lowered a microelectrode with a tip of, was very small. It was not 1 micrometer, but it was closer to that. into the brain of anesthetized cats and presented these cats with some moving bars, some moving gratings. We're going to go through this experiment on Wednesday morning, but what I want just to tell you is that if you lower an electrode like that into the brain, you're going to be able to pick up the activity of neurons of the brain. But because the tip of this electrode is very thin, at most you will pick up signals that happen very close by to the tip of your electrode. Since the tip is much smaller than one neuron, which typically is around 30 microns, you will pick up basically signals from just one neuron in this case, which is cool, but also is not very efficient. You have one animal or one experiment every time you put your electrode in, right? It's not the way in which today we're going to be recording from hundreds of neurons at the same time. So most recordings of activity in single neurons, though, were made in this case, in animals that were anesthetized with microelectrodes. How can you record from more than one neuron per time? Find bigger electrodes, right? Get big electrodes that you put inside the brain of the animal to record a lot of neurons at the same time. You have a problem, though. The brain is a very dense tissue, and neurons are packed next to each other. When you lower an electrode into the brain, you most likely are not going to listen to the activity of just one neuron, but you're listening to an activity of a lot of them at the same time. So what you will get from these type of recordings, in which you have a large electrode inside the brain, it's something like this, right? Everything that crosses this red threshold here will be considered as a spike. But in this case, how many neurons contribute to these spikes? You really have no idea. At this point, you cannot really tell, right? Because the waveform might be different, but it depends from so many factors that you cannot really tell. You can try to use some computational method to sort this neuron, and that's what people have done to give you the answer that these are actually the 3 neurons that are fighting here, plus this other bunch of neurons that are basically in the vicinity. In fact, when you have an electrode in the brain in this configuration, you're recording from 3 different areas. The areas that is immediately close to your electrode, you're going to be able to record activity from individual neurons, and these waveforms are stereotyped enough that you're still going to be able to separate them, even if not extremely precisely. You will record activity also from the neurons that are surrounding this ball, that is basically this ring here, but those will be so unreliable that you're not going to be able to cluster them together and to say this comes from this neuron. Usually, this is called multi-unit activity, and it's something that you sometimes consider as noise. Sometimes you do some studies of that. And then you will record activity that comes from all these other neurons that are around the electrode, right? It's not really activity that comes from the soma, but from this neuron, but you will be able to record this, which is proper noise, and it's called neuropil noise, from the dendrite and axons of this neuron that are in this area 3. So in the end, you have a very hard time identifying these spikes here and say, okay, neuron number 1 was active at this time, neuron number 2 was active at this time, neuron number 3 was active at that time. However, we can use a trick. And the trick is what I told you before. The trick is that the shape of the waveform depends on the orientation of the electrode with the cell, right? So if you have 4 small electrodes, each of them are at different distances from the neuron that you are recording from, each of them will record a different waveform that depends on the relative orientation between the electrode and the neuron, right? So imagine that you have 2 different neurons, the red and the green. The red is active at this moment, the green is active at this moment. If you look at the 4 different electrodes, they will record the same event with 4 different waveforms. And the same things, the same electrodes will record the events of neuron number of the red neuron in exactly a different way. So we can use the property by which the shape of the waveform depends on the spatial orientation between the recorded cells and the electrode to actually distinguish neurons from each other, right? What we do is basically to triangulate the location of the neuron and assign different waveform to specific neuron based on the properties of the waveform that is picked up by the different electrodes. Is that clear? Because if this is not clear, we cannot move forward. Okay, I assume it's clear. I'm going to tell you then one of the cutest invention in neuroscience in the 70s and 80s, which is the tetrode. The tetrodes takes advantage exactly of this principle and exactly of the configuration that I told you before. The tetrode takes 4 different electrodes and twists them together so that you create just one big electrode, which is called the tetrode, in which there are 4 different channels. So usually this is 4 thin, usually it's 12 microns, so it's not 1 micron, but thin electrodes that are twisted around each other. This is what the tetrodes look like. I don't know if this is, actually this is a very good picture because it's very thin, but you can see that these are the 4 electrode tips. Do you see my mouse, what is pointing? These are the 4 electrode tips, and these are twisted around each other. And the way in which you make them, apart from being extremely relaxing, but you literally take this 12 micron thick electrode wire and you start turning on top of each other. You will have movies later to see how this is made. I really suggest you to go and look at them. It's really cute. It's really ingenious. And it created very big advances in the way in which we understand the brain. Why is this extremely important? Because in this case, you can have this arrangement here. You have 1 tetrode, you have 4 electrode tips, and you have 2 neurons, A and B. Now, if you look at the relative orientation of neuron A versus the 4 different electrodes, you see that neuron A is closest to the electrode number 4 and number 2, but further away from number 1 and number 3. And in fact, when you look at the activity of, let's say, the waveform of the extracellular spike of neuron 1, it's going to be very large on tetrode 4, very large on tetrode 2, but quite small on tetrode 1 and 3, right? At the same time, neuron B is going to be the opposite. So the mirror image is going to be very close to tetrode 1, so electrode 1 and 3, but farther away from 2 and 4. So when you go and record the activity from this neuron, you have the largest deflection on electrode 3, the second largest on 1, and then 4 and 2. So in this case, because these 4 electrode pick up something that is completely different from 2 neurons that are oriented differently to the tip of the tetrode, you are able to triangulate and to basically assign each trace, each spikes to the individual neurons. You're still going to record from different areas, but in this time, in what before I had called as neuron number 1 or number 2 is area number 1 or number 2, you're going to be able, for a radius of, 50 microns, to assign in a very specific way spikes to individual neurons, based again on the fact that this neuron, the length of these vectors that connects the neuron to the electrode tips are going to be different for different neurons. The only case in which you might have 2 neurons that have exactly the same profile is that if these 2 neurons were absolutely on top of each other, which is something that it happens extremely rarely, but you have to factor in. So we'll see later how we can actually distinguish that situation as well. Okay, so this is the way in which the tetrode works. In order to record these tetrodes from the brain of animals, you don't work in isolation. You have to create a tetrode bundle and you create a drive. So this is in the video that you're going to be seeing later, but I'm going to just tell you the principle here. So what you do is that you take basically multiple tetrodes. You can put up to 30 tetrodes or even more sometimes. Building them is really an art, and there are labs that are amazing in that, into a sort of these days, these are 3D printed plexiglass or plastic casing in which every electrode of every tetrode is basically soldered or attached to the pin of a connector, which is basically able to pick up and read the electrical signal that the tetrode is picking up, or the electrode in that case is picking up within the brain of the animals, and transmit it through a series of cables to a series of amplifiers. These signals are extremely small. You need really to amplify them in order to make them visible and to hear them. Of course, there is a lot of interfaces, and you see it from here. This is, for example, one example of a rat that is implanted with a very big hyperdrive, in this case, which has multiple tetrodes. The pins are connected to cables. The cables are connected to the amplifier. The amplifier is connected to your computer, and you see the stream of beautiful information that is basically like picked up and registered in your computer while the animal is doing stuff. Okay, these things tend to be quite heavy. That's why the largest one are usually for rats, but we have a lot of different type of drives also for mice, and that's what we use in the lab to record single unit activity from multiple neurons at the same time in alive and freely moving animals. Okay, now if you were here and you were in the Biocentrum and we could be all together in a room, I would probably set up something to show you how to organize this. We are not at the moment doing this in the lab, but it's definitely something that we're going to set up during this year because it's a powerful way to understand how neurons actually encode stimuli that they feel in the world, or also cognitive maps or mental maps like the one that they use to make memories, right? Since we cannot do this, I really suggest you to go and watch these two Jove papers. These are extremely short video, like 10, 15 minutes, but they really show you how you build these things. I had never seen something like this before I started my postdoc. I can tell you that they're really cute things. And if you see them, I'm sure that you want to make some yourself. So use your VPN, connect to the Biocentrum, open these two videos and spend half an hour of your time. Okay? Now, recording the signal is just one part of the story. You have lowered your tetrodes, you have put them into this area, you're recording from a lot of neuron, and this is what you get. A change in the potential, not in the membrane, but in the potential over time, right? These data reflect the current that flows in the extracellular medium over time that is given by synaptic activity. It's not a direct measure of the action potential again. It's not as clean as the intracellular recordings, but most importantly, is given by the sum of two contributions. One is the spikes of neuron that are in area 1 and 2, with the caveat, as I said, that spike 1, you can really resolve them, spike from area 2, you cannot resolve them. And then it's the local field potential, which is basically like the activity that comes from the profile of changes in the membrane potential that comes from the activity of all the other neurons into your area. Right? That will give you some sort of signal that rides on top of your spikes. So now the art starts of separating what is actually signal, what is actually spikes in this raw data. And I want to highlight you the steps that I've done so that you can understand what we talk about when we talk about spike, when we talk about what we talk about local field potential and so on. Okay? So the first thing that we do is a bandpass filtering. We know that spikes are extremely fast events that happen at a frequency that is very high. So what we do is that we decompose this signal into the low frequency content that goes from one signal that has a frequency of 1 to 100 hertz, in which the local field potential will fall, and the high frequency context in which have the spiking activity. This raw data that we get is really the sum of this contribution plus this contribution. But now one thing that you see immediately here is that on this contribution, you have eliminated a lot of fluctuation of this trace, and you can set a threshold and define everything that crosses this threshold as an individual spike. Okay? This is what we focus to understand the neurons, the activity of individual neurons. But we really do not trash this information here. This is a bonus that I just want you to keep in mind for 30 seconds after I finish and then cancel if you don't want to hear. You might have heard that our brains have some internal rhythm, that neurons seems to be active at certain frequencies. For example, you have gone to the doctor and you have started to do EEG or whatever you want to do when you record basically the brain activity. Neuron oscillations are repeating activity patterns that can be measured when the electrode is in close proximity to the nervous system. In the brain of humans, it can also be recorded if you have electrode directly on your scalp, not directly on your brain. So when we get that recording there, so the EEG that we get from the scalp, it's exactly this component here that is large enough that we can actually pick it up from the scalp itself. These are what are called rhythms of the brain. We know that they are composed, they're not just one single trace, but they're composed by different oscillatory patterns that happen at different frequencies and that are prominent in different phases of your behavior. So when you're asleep, your basically brain oscillation have a frequency, or this LFP has a prevalent oscillation that goes in a frequency between 0.2 and 3. When you're deeply relaxed but still not sleeping, your brain oscillation is between 3 and 8. When you're relaxed but still alert, you have between 8 and 12. And when you're alert and focused, your brain oscillates with a frequency that goes between 12 and 27. This is something that is extremely important for the brain itself, is a way in which the brain organizes activity and flow of information from different areas. Okay, now you know, you can forget it. We're not going to talk about it again into this week. If you want to know more about this, drop me a message, talk to me, come to the lab and see stuff. Okay, now we have isolated, remember, I just want you to remember, we have isolated this signal here, right? Now our point is to find these spikes and assign these spikes to individual neurons. How do we do this? The first thing is we identify the spikes. We identify the spikes because spikes have a specific profile. Do you remember the profile that I showed you before? We try to look for everything that fits how we think a spike should behave, which means that we will lose some, but it's basically like the part of the game. So we create a model of what the spikes look like, and we isolate these individual events to basically consider them as spikes, right? And then we end up with things that are isolated like this and like this. What we end up in the end, it's some sort of smoothed signal in which we have a deflection of this waveform that is different for our 4 individual channel in 1 tetras. The task now is to say all these spikes belong to neuron number 1 and all these spikes belong to neuron number 2. To do that, we analyze the shape of the waveforms. So the waveform has, in this case, you see the reverse indication, has a certain rise phase, a peak, a distance between the rise and the decay, a certain profile of this exponential decay that you find it here, a rest as a different of, let's say, quantifiable properties that we can extract number with, and we can use to separate spikes from each other. So the spikes that basically like all follow with the same profile clustered together in a dimensional space in which they basically are going to, in which we project them once we do some sort of dimensionality reduction approach to this type of data. Again, you don't need to know the details of this. What I want you to know is that we isolate spikes, we quantify properties of these spikes, okay? We quantify properties of these spikes, and then we use this property to separate spikes in cluster. At that point, we do a little bit of a trick because we say that the spikes that fall together were fired from the same neuron. This is not entirely precise, meaning that we have no way to say that actually these spikes, these spikes are slightly different from each other. If you see here, these are all the spikes that are classified here as blue. There's still some differences between each other, right? It's not entirely exact that we say this cluster here is neuron number 1, neuron number 2, neuron number 3. We actually define these as clusters, but it is a good approximation. And we can use this, but we can actually say how clean our clusters are and inspect our clusters are by leveraging one property that you have seen before, which is the refractory period. We know that one neuron cannot fire twice at a distance of 1 millisecond, 2 milliseconds, because it's in its refractory period, right? So if we have in a cluster 2 spikes that happen at a distance of 1 millisecond, we know that these 2 spikes must have been fired by 2 different neurons. And usually how we do that, we quantify how many times 2 spikes that we have isolated as coming from the same neuron are at the distance of 1 millisecond from each other, at 2 milliseconds from each other, at 3 milliseconds from each other. And we plot it here as a correlogram, right? That tells us how many times the neuron was fired at the latency, the 2 spikes were fired at the latency of less than 2 milliseconds. If we have a lot of spikes that fire at the latency of 1 milliseconds, then we know that our cluster is very dirty. And we're going to do what we know as cluster cutting, that is basically like reassign spikes by separating the spikes according to different variables in order to get cleaner and cleaner clusters. This, again, it's something that right now is completely automated, but it's something that one can do also very much do by hand. And Vilde knows something about this. She has done a lot of cluster cutting during her master thesis. It's basically something quite cute, but at the same time is a little bit time consuming. Just to show you, this is neuron blue, this is neuron red. If you do the autocorrelogram, you see that at the latency that is minus 2 milliseconds.
Do people still see the presentation?
Okay, so.
Sorry.
Okay, 1 second. It seemed like it fell down. So Do you see it now?
Yep. Yes.
Okay. Did you see this before? Okay, let's go a little bit back then. You remember this? Okay, so we use the properties of the spikes. This is what I was mentioning. When we use properties of the spike to separate the spike from each other and understand the spikes that look similar to each other, right? And we assign spikes that look similar to each other to the same cell. This is what we associate as cluster here. And what I was telling you before is that it's very difficult because, for example, spikes that look like this are very similar to spikes that look like this. So there is a certain amount of noise in our cluster assignment or cluster testing. And what I was telling you before is that at this point, we decompose the signal that we found in the activity trace of 3 individual neurons, right? And we are even able to find instances in which neurons fire close by to each other. We call them collisions. You don't need to know this. Just to know that, like, by plotting the shape of the spikes into a multidimensional space and using dimensionality reduction technique to actually project this multidimensional space into a lower dimensional space, we can separate spikes that look like each other and assign them to individual neurons. This is what I was telling you about the spiking, the firing of the spikes at very short latencies from each other. If two neurons, if the clusters is very clean, so all the spikes come from one neuron, you should never find two spikes that fire at less than 1 millisecond from each other, because those are, or 2 milliseconds actually for excited neurons, because those fall in the refractory period of the excited neurons. On the other hand, if you look at spikes and compare the spikes of the red versus the spike of the red versus the spike of the blue, you find the profile that is like this. There is a lot of pairs that have a temporal delay that is lower than 2 milliseconds. In this case, it means that these spikes will fire from two different neurons. Okay, so in the end, when you want to analyze your tetras, you have the raw signal, you decompose, do a bandpass filtering, you isolate individual spikes, and you quantify the properties of these spikes so that you can extract the features of these spikes and plot in a multidimensional space that allow you to cluster spikes that look the same and assign spikes that look the same to individual neurons. So in the end, you end up with something like this, which is you've recorded from 25 neurons at the same time for a certain period of time. These might be seconds, for example, and you see that each neuron has a different profile of activity. Some neurons are silenced throughout, some neurons are very active, some neurons are active in some moments and some not. What does that mean? We'll understand what this means on Wednesday. For now, tomorrow, we are just gonna be understanding how you create temporal profile of activity by the way that you connect neurons and by the stimuli that you get. Okay, so this ends the part about what I wanted you to get from this day. Today was mostly to refresh some of your knowledge about physiology, electrophysiology, the way in which neurons talk and communicate with each other. This was a way to understand what principle induce a neuron to fire or not fire an action potential, dendritic integration, how we can study this in alert behaving animals to try to make sense what actually the neuron says and how they actually support complex behaviors, like creating memories, like perceiving an object, like perceiving a face, or even create an idea that is very conceptual in your brain. We're gonna go through this on Wednesday, okay? So what did you learn today? I'm gonna put some bullet points, but please feel free to chip in. You might be exhausted from not realizing that you could not see the presentation before, but I want you to take home some messages which are important. Neuron communicates by means of electrical signal, the action potential, that propagates along axon to induce release of neurotransmitter at the synapse. Neuron transmitter binds to receptor in the postsynaptic neuron, and this causes the depolarization or hyperpolarization of the membrane and a transient change in the membrane potential. IPSP and EPSP interact with each other, and if there's the summation of their effect crosses the threshold to induce the action potential, you have an action potential that is transmitted along the neuron and is fired at the level of the axon. Summation happens in space and in time. So the way in which neurons are connected to each other influence a lot the message that the individual neuron broadcasts to neural networks. And we're going to go through these in details tomorrow. The last is that we can record the activity of neurons while animals perform any type of task, sensory task, cognitive task, motor task, by implanting small electrode in the animal's brain. Okay? I want to leave you with just one question. You have played around with the Hodgkin-Huxley model. Is it a good model for how a neuron works? What do you think? There were some questions. Yeah, go ahead.
I think not really,
Mm-hmm.
because we're always talking about one stimulation at one point with one setup. But in reality, there is an input and every time from other neurons and they're a huge network. So it's not that, how to say that, yet the platform you get one input and one output. That's not how it works in reality.
Yeah, this is definitely one point. And this is one point that I want to discuss later on too about the model. Did you see any things that you were not expecting during your simulation? Something that looked really strange to you when you started when you went through the exercises?
Well, as you previously mentioned that the model was created while not much was known about the precise structure of the membrane, thus the channels are more like an assumption.
Exactly. So what Anna is referring to is the fact that when you have modeled and left only the leaking or the passive sodium channel, you have seen something that really didn't really quite fit what you were expecting, right? You saw that the membrane was immediately going up to the reversal potential of sodium. And this is something that highlights one point. So I just want to give you a little bit of historical background. The model was put forward in the 50s as a mathematical model that consisted in a set of differential equations that were necessary to approximate the features of excitable cells, like neurons, and to describe their working, right? To describe the way in which the membrane potential was changed and how it could propagate the message through means of changes in the electrical flow of ions through a semi-permeable membrane. It is still considered one of the greatest achievements of the 20th century biophysics. My question to say it's a good model of the neuron is quite provocative. In no way I'm saying that the Hodgkin-Huxley model is bad. It's actually great. Hodgkin and Huxley got the Nobel Prize just 10 years after their model was put forward, which is in Nobel Prize time is extremely fast, because that really brought us to model a way in which excitable cells are able to create electrical signals and to propagate these electrical signals in the body, right? And what Anna was mentioning before, so however, let's see the pitfalls of that. It does not take into consideration different type of ion channels. In particular, it does not take into consideration that some channels might need a ligand to actually be bound in order to be open. And this is what we were mentioning before with Anna, the fact that the leakage channel is modeled in the model as a passive type of current, not even a channel, right? And that was necessary because it was taking care in the model to create a situation of equilibrium in a resting state that could be changed by the application of a stimulus. So that was the role that the channel was making into, that particular current was making into the particular model. It wasn't really to model the activity of the sodium channel, because as Anna was saying before, we discussed in the group, the physiology of the channel was actually unknown at that time. So they knew about the voltage-gated currents, but the exact physiology of the individual channel would come much later. It only considers some transporters. We have seen before that transporters are extremely important for creating this gradient along the two sides of the membrane. In the model, there is a certain stoichiometry that is 3:2, which is based on the sodium-potassium pump, and little else. We know that there is a lot of mechanisms that are actually all impinging and creating into this equilibrium. What Fabio was saying, that it doesn't take into consideration the complex geometries of dendrite and axons. It doesn't take into consideration the fact that, you know, there is a lot of different contribution and it's not just a single point injection. However, it was never the intention of Hodgkin and Huxley to model how the neuron works. Their intention was to model how electrical signals like action potential are generated in excitable neurons like neurons and myocytes. It became very important for the brain because it allowed neuroscientists to make predictions about how the action potential was generated and the way it propagated. And based on those predictions, they could guide those experiments that had to take either another 20, 30 years until Erwin Neher and Bart Sakmann invented patch clamp and could actually be able to study in depth the physiology of individual channels. So this is something quite general. I told you in the introduction before that the goal of system neuroscience is to make a model to just test your hypothesis. That is true, but this is not the end of the story. You make a model based on evidence. So you start with framing a question, you try to create a model based on the activity or the experiment that you have seen. You test that your model actually works, and then you say, okay, this is my model. The model allows you to create experimental prediction that then you can go into the model itself, into the biological system itself and test. And if the experiment don't turn out as your model would predict, then you have new data, you have to formulate new hypotheses, and you have to update new model. So there is always a it's a circular way in neuroscience, right? You use data to create a model, you use your model to guide the acquisition of new data. And this is something very, very actual, actually. On Wednesday, we're going to talk about the cognitive map. We're going to talk about grid cells. We're going to talk about place cells and speed cells. There is one type of cells, the speed cells, whose hunt, if you want, or experiment started because their existence had to be predicted by the model of the grid cells. And in fact, they were discovered almost 10 years after the grid cells, even though probably the correlates are a lot easier to understand than what the grid cells are created. But hold your thought until Wednesday to understand it. So I just wanted to make sure that it was very clear in your mind that the model, it's an approximation of a biological phenomenon that is used to test prediction that you have made or hypotheses of how things might work, but is also used to guide your additional experiment that needs basically continuous confirmation in order for the model to be taken as truth, as granted. Okay? Right, so it's finished for today. Today we went through everything that we wanted to see. I think we have time if there are burning questions, comments, ideas put forward. Now is the time to do it. Now is the time to wake up and tell us what you want to know about physiology.